right, so here's the deal. Up until this point in your life, and you've been in chemistry, in this class or honors chemistry, we typically just have an arrow going forward for reactions. But really, most chemical reactions, or even physical changes, like this is a physical change from liquid to gas, they actually go both ways. Like liquid water can evaporate and turn into water vapor, but water vapor can also condense and form liquid water. It goes both ways. And so if I'm dissolving salt, you have to understand that when salt dissolves in water, if this is salt and I put it in water, yes, it dissolves, but at the same time, some other particles are actually joining back together to become salt again. So is equilibrium, yeah, it's fun, right? You have to understand that it's not just going one way. It's not just going reactants to products. Some products are actually turning back into reactants. But when it's finished, when a reaction looks, quote, finished, not really finished, it's just the rates of the forward and back, forward and reverse reactions are the same. So let me kind of get into that a little bit more. And your homework that you have to do has some really good animations and videos on that principle. So that will help you. Reversible reactions are good. They keep you alive. For example, hemoglobin in your blood contains iron, and the iron will bind with the oxygen and then release the oxygen. But hemoglobin, that's your red blood cells. They're red because iron is red when it oxidizes. Yay, rust. Okay, got it. Good times. I'm sure there's more to it. I'm not a biologist. But hemoglobin in your blood, that's not like an element, but that's just they're being lazy. Hemoglobin in your blood combines with oxygen, and then your red blood cells are oxygenated. Okay? But then that oxygenated blood goes to your cells, and then it can release oxygen at that point to your cells so that you can run or think or breathe or whatever. And so that's good that this is a reversible reaction, because then your blood is pumped back to your lungs and then it can pick up more oxygen. So it goes both ways. Isn't that fun? You can tell I'm like just slowly sliding into this, right? It's fun in the blood. Okay. That's when the PowerPoint starts with talking about blood, that is what is it, ominous? Yes. Ominous. I messed it up. Okay, so funny thing about me is that I mean I knew that word ominous. I don't know the word.
I think you're thinking like omnipotent.
Omnipotent, yeah.
I know, but some people pronounce it like that.
No, I'm wrong though. Like
It's okay.
ominous. It's ominous.
We can move on past this.
You know, we're learning all kinds of stuff today. It's fine.
Fun fact, she already looked this up and like saw how this.
I've apparently been screwing this up for a couple years. Don't judge me. You need me. You need me. Some reactions really do kind of go to completion, where the reverse reaction, where reactants go, products go back to reactants. That doesn't really happen a whole lot. So like if you took the reaction for, the combustion of a fossil fuel, like really the carbon dioxide and the water aren't really turning back into oil or gasoline. So some really do go just the forward direction, but most of them, both processes are happening simultaneously. So let's look at that. So N2O4 can be forming into 2 and O2s while these are going back to N2O4. Now let's look at this, okay? This is what we've already talked about. This is tied to kinetics. What I see here is I see the reaction as it occurs, and I can tell that NO2 is the reactant because it's getting formed, and N2O4 is a product. Did I say that? Oh, excuse me. NO2 is the product because it's getting formed. I said the wrong word. And then N2O4 is a reactant because it's getting used up. But you can also tell just intuitively that equilibrium happens right here, and those concentrations are staying the same. See it? And so to our naked eyes, that reaction would look finished. But it's not really finished. What happens if I go to this next slide is that the rate of the forward reaction and the rate of the reverse reaction, when they are actually equal, that is equilibrium. So if I could just use my little blocks because they help me a lot. If I have, A and B coming together, and that's my reaction, and I get some more blocks, and I have a whole bucket of them. At the same time, those are getting formed. Maybe some other A and B's are coming apart. But then, this happens, right? And then this happens. And so nothing is really changing. If I had, billions of particles, it would look like nothing was happening. But at an atomic level, they are rearranging, but it's staying the same as far as what we see. That forward and reverse rate are the same. So anyway, moving on. Equilibrium, like I said, the forward and reverse reactions continue to take place. The rates equal, but the concentrations of each are not equal generally. They can be, but generally they are not. It is the rate of the formation that is the same. So, happens in a closed system. Okay, so this is where it starts to look like what we just did, but it's not the same. Okay, so writing an equilibrium expression is really not that bad. What you have is a capital K, which has nothing to do with the lowercase k that we just used. This is completely different, okay? This is a different thing. So capital K is equilibrium constant, okay? The K that we already did, I'm just trying to make it make sense for you. I wish someone had done this for me, so I wouldn't have to stay up all night last year. So this little K is a rate constant, okay? It is what it is. And it had a unit, and we could figure out the units. This K has no unit, and it is the equilibrium constant is a capital K. So it's not the same. They have nothing to do with each other. Well, you'll be able to tell because how you write the expression. So do you remember our exponents here had to be experimentally determined when we had to either use a chart or look at a graph, right? That happened, okay? But here, this is actually kind of easier. What you do here is the exponent is actually just the coefficient. So notice here too that it is products, the concentration of the products, and those brackets are concentration. Products go on the top, and they are raised to the power of their coefficient. So if this was 2, 2, and then it was, sodium ions, then it would just be Na in brackets, and yeah, you put the charge, and then you'd square it. Whatever. It's not the worst thing that's ever happened, right? It's fine. And the cool thing is, I guess, you should be suspicious about this. If you look on the formula sheet, it has this formula. Kc is equal to C raised to the power of C, D raised to the power of D, A raised to the power, and it gives you, it actually even gives you like an equation so you can tell which is products and reactants. So you can't screw this up unless you just don't take the time to look at the answer sheet. Or not the answer sheet, the formula sheet. Yeah. It's fun, right? And like I said, this is the equilibrium expression. And so the reason this is a lowercase c is because it's we're talking about concentration, and you can tell we're talking about concentration because you have to think hard. Just kidding, because you have brackets, so that means molarity, which is concentration. That's how you can tell. How you go. All right, so let's look and see how we do this. All right, what does this look like with a real reaction? So I'm just going to do this one for you. It's always going to be K. Just like with the rate law or anything, you need to write the whole expression. So Kc is equal to the concentration of nitrogen monoxide. You don't have to put the states in here, so you don't have to put a G or anything. And that's going to be squared, and that's going to be over nitrogen gas. And it doesn't get an exponent because it doesn't have a coefficient. Well, its coefficient is 1, And that's it. That's the equilibrium expression for this equation. There's several catches, but this is, let's just feel smart right now. Let's do it. Yeah, you can do this. Now, the good thing is, true story, those really long FRQs, the ones that are worth 10 points that are at the beginning that you really don't know how to do yet, like these are where that comes from, the rest of the year that you have with me. The first question will be like, write the equilibrium expression for this. The first question will be that, like 1A. You can get a point for that, right? So you can do that. That's your 1 point. Cool. So that's fine. Good times. So there it is. Whatever. No worries. Now here, let me explain. So this is where it starts to get fun. These are concentrations, right? These brackets means concentration. So here I have solid nickel. Let me ask you a question. Can I change the moles per liter of nickel? Am I going to change the amount of moles in a liter of nickel? No. has a constant density. So you don't, so it's not going to change equilibrium. It's not going to change anything. And it's not, doesn't need to be written in here because that's kind of a constant thing. So solids do not go into the equilibrium expression. Still products over reactants, but notice the two solid species are not in the equilibrium expression. Huh? That's what? Sad? Yeah, well, there's more left out. Okay, so. So this is what I was talking about. They have the same density, the same particles per unit, so we're not going to put solids in. Also, liquids do not get put in because these liquids, again, the moles per liter are not going to really be changed. And then also, these reactions, aqueous reactions, when we have an amount of water and then we have these small number of ions in the water that are reacting, the amount of water formed or present isn't really changing anything. So it's not of significance enough to put in the equilibrium expression. But if you don't like all that, you can't keep it straight, it's only gases and aqueous things. So it just spells GAC, okay? GACs go in there. GACs go in equilibrium expressions. So that looks like it's part of GAC. That's GAC. That's GAC. That's not. Oh, that's all. So now still I have products over reactants, and those go in. Aqueous things and gases, that's it. Now let's just pretend for fun, because this is fun, let's pretend that this was a liquid. My equilibrium expression would just be 1 over that. So I don't have any products that go into the equilibrium expression. So if that was the case, it would just be 1 over HCl4, or raised to the 4th power, and then O2. Or conversely, if it so happened that, you know, this was a liquid, and this was a liquid, then my equilibrium expression would just be that. There's no problems. You don't have to have a bottom to the fraction. And really, that's a 1, and it doesn't matter. Right? All right, so what I want you to do, I'm going to give you 5 minutes, and I want you to work. You can skip number 1 in the practice, but we're going to go ahead and look at number 2. Let's get as much of number 2 done in this 10 and 5 minutes, okay? I'm just going to pause the video, and I'm going to put up the answer key for number 2 so you can kind of check as you go. You have to write out the whole equilibrium expression, which is to say that you need to write a capital K, a little c, and an equal sign and the rest, okay? Make sure I start this back. Oops. That's for concentration. So if we're given molarity, Kc is what we're going to use. I did say that liquids are left out. Like I said, adding or taking away small amounts of water doesn't really change anything. Doesn't really change the overall concentration of water, for example. So again, it just is GACs, G and AQs, GACs, okay? No liquids or solids. For gases, if we throw back to gas laws, unit 2, you recall that the gases are given to you in ATMs for pressure, right? Typically. And so do also recall that if we have 0.2 ATMs of hydrogen and 0.5 ATMs of oxygen, the overall pressure would be 0.7. That's Dalton's law of partial pressure. Are you remembering what I just said? All right, so sometimes with gases, and most typically, honestly, with gases, instead of them giving you the molar concentration, the molarity, they'll give you the pressure in ATMs. And so if they give you pressure instead of molarity, this on the formula sheet, let's go look at that, there is a Kp expression. So the Kp expression, the equilibrium expression, if you're given pressures, notice it has a pressure of C raised to C, U to D. And so what does all that even mean? It just looks like a hot mess. Let me show you. So what we're going to do with that is, like, if we just, you know, make water, hydrogen gas and oxygen gas, and then, you know, that's the first time you'll see that in 2 waters, right? And then that's actually gas too. So if I want to write the equilibrium expression for this, if they give me pressure in ATMs, what it's going to look like, can I write that in those squared brackets for molarity if I'm given ATMs? No, because it's not molarity, so don't do that. You won't get any points. Yay! So you have to make sure you use parentheses that are rounded instead. So it's still the same. I'm going to go Kp. And if I was, like I said, given pressures instead of given molarity, still it's going to be the products over the reactants. And so I'm actually going to go capital P for pressure. That looks like a weird P. It's a normal P. P for pressure, and then I'm going to go like a subscript of water. So the pressure of water squared, same thing, same ideas, over, parentheses, the pressure of hydrogen, again, that's going to be squared because the coefficient's 2, and then the pressure of oxygen. And so the equilibrium expression is very much still written the same, but you're using rounded parentheses, and you're going to, everything's a P, you're going to subscript of your gas. On the answer key, they did a kind of terrible job with that, but I'm sure I'm right. As far as like they wrote the gas big, and it should be a subscript, and you can see that very clearly on your formula sheet, and actually even on their form. So anyway, so let's go ahead and look at that. So yeah, you see what I'm saying? It's little numbers, or little letters. Partial pressure, like I said, if we add those up, we'll get the total pressure. That'll come into play with some math tomorrow. Yeah. And so again, remember going to the kinetic molecular theory, back to that, all gases are going to exert the same pressure if I have a mole in a certain size container, and then, you know, doubling the moles doubles the pressure. That's Avogadro's law, but that's just, yeah, going back to stuff. We don't have to do this. It's on Chemistry Olympiad, but you're either going to be dealing with Kp with gases, they'll give you ATMs, or they'll give you molar concentrations and you'll do Kc. You won't have to convert between both, but if you do have to, that's the conversion, but we don't have to do that. So what we're going to do for this one is we're going to write the equilibrium expression. Let's just read it. And so let's see which one we're going to do first. Find Kc and Kp. We don't have to do one, okay? For the falling system at 427 degrees Celsius. Well, why do they even give us the temperature? Do you remember how the K for rate constant changed with temperature? It also, this capital K, the equilibrium constant, changes with temperature as well, because it's going to speed up a reaction. So anyway, if the equilibrium concentrations are 0.140 molar hydrogen gas, and then bromine is 0.019 molar, and then hydrogen bromide is 0.395 molar. If I have all that, I mean, am I going to do Kc or Kp? Kc, right? And so you could convert it to Kp later, but we don't need to do that. So let's go ahead and the first thing you're going to do, don't let's freak you out. You got a bunch of numbers, who cares? It's fine. What we're going to do is we're just going to write Kc, and you're going to always start these questions by writing the equilibrium expression, and then you're just going to fill the numbers in. This is like cool. This is easy. So I'm going to have HBr in the squared out brackets for molarity. It's going to be raised to the second power because the coefficient's 2. And then I have hydrogen gas, and I have bromine gas. So, okay, that's not a big deal. Now we're just going to fill in those molarities and then punch buttons on your calculator, and then you'll get what the equilibrium constant is. That doesn't sound so bad, right? So I'm just going to fill in my numbers that they gave me. HBr is 0.395, and it's going to be squared. So my calculator, I'm going to hit the second button. And then down here, I'm going to go 0.140, and that's for hydrogen, and then bromine 0.019. And so just punch buttons in your calculator and get the answer. I don't remember, like 59 or something. All right. Is it 59? Okay. 2 sig figs because this one has 2 sig figs. So your answer can only have 2 sig figs. So when you get your answer, Kc is equal to 59. This number is mathematically significant, and I will explain that to you. So, do you guys remember how at the beginning of this PowerPoint I was like, the concentrations of products and reactants at equilibrium are not the same, the rate's the same? Okay. This number is 59. Think about what goes on the top of the fraction, what goes on the bottom of the fraction, as far as reactants and products. Right? Talk to your group if the answer of the equilibrium constant is 59. Mathematically, What do I have more of at equilibrium? Talk to your friends. The answer is a product or reactant. That's okay.
Oh, I was trying to say. I was thinking product. I didn't know what yeah. Yeah. Yeah, that didn't make sense.
All right, so what at equilibrium do you think I'll have more of, products or reactants? Sarah? Okay, and mathematically, let's prove that to ourselves. When we divide, I'm just going to make this go away. When we divide products divided by reactants, how could we get 59? Oh, we could get 59 by saying 59 divided by 1, or, I don't know, 108 divided by 2. Right? So, guess what's more? Definitely the products. So, what that means is at equilibrium, when I have my sample at equilibrium, I'm going to have more products made than I have reactants left. That's what this means. This means something, and you have to understand what it means. So, I have little cheaty ways to remember this, of course, but I do want to explain the math as well. So anyway, there's KC, and that's what we got, and then it's a quick conversion to go to KP. But here's the deal. This is how I think about it, okay? Whoops. Sorry. This will actually be important tomorrow when we throw in more letters. I'm smiling at you. You see it? Okay. So if I think about this being on a number line or something, and K is equal to 1, if K is equal to 1, products divided by reactants is 1, so they would be the same, wouldn't they? Okay. So anyway, if I have a reaction of A, B gives me A plus B or something, I don't know. If the equilibrium constant is less than 1, then equilibrium is going to be little, equilibrium constant is little, and it falls to the left. So if the equilibrium constant is less than 1, little to the left. So if my equilibrium constant comes out to be 0.0020, then reactants will be favored. Reactants are on the left, little to the left, okay? If you're taking a test and you freak out, like, that's a quick answer, okay? And so if the equilibrium constant is larger than 1, or really like larger than 10, then it's going to favor products over equilibrium. So, little to the left, got it? All right, and then mathematically it also makes sense. So this is the little to the left, and so if you think about how would I get, this is a penny. Think about math, okay? If I wanted to get a penny, well, I guess I could take $1 and divide it by 100. And so I guess $1 is smaller than 100. And so this would be mostly reactants. Reactants are what's on the bottom. Do you follow my math there? I'm trying to make you better people right now. Okay. And so here is a recap of what I just said. And one would be about equal amounts of either, and equilibrium will lie in the middle. So the last thing I want to do today, the reaction is, and I'm going to write it a little bit bigger because I'm about to zoom in on it, AB and then AP. I wonder why I wrote that. So talk to your friends. I'm going to zoom in on this picture and then turn the light out for you. What do you think my equilibrium constant would be? And so when I say constant, you should think letter K because that's, why I make it C, because that would be too easy. What would the equilibrium constant be? 1, less than 1, larger than 1. Good. I saw a man counting circles. Thank you. We can mathematically determine it by counting circles. Sad. I think that's the whole thing. Yeah, that's the whole picture. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 14,
Yeah.
16, 17. Is it 17? Can you count it? Can we say it's 17?
That's good.
Okay, great, thanks. And then was it one of each?
It's two.
Okay, so when we do this, we're gonna get 4 divided by 17, which is like about a 4. So like 0.278. But it's gonna be less than 1. And so little to the left, it favors reactants. But then graphically, picture, you know they're gonna throw up some pictures of a circle. I know there's pictures of a circle on my test because I just printed it out. It's just like this question. So we look at circles, obviously the reactants are favored, and that would mean that the other way of thinking, K is less than 1. How you feel? I'm just gonna leave you with that today so you feel smart for a minute. And y'all can do 1 through 7, 2 through 7, skip 6B because it has the conversion from KC to KP. Unless you just feel like doing that. And I'll let you guys go ahead and take the answer key because tomorrow we'll use the rest of it. So anyway, let me go ahead and let you guys take that. I'll try to turn off the little video for you so you don't have the X in the middle. To be continued tomorrow.